Hello there, and welcome back to Bedtime Science. I am really glad you are here tonight. For a moment, notice the surface beneath you. A mattress, a pillow, perhaps a sofa or a chair. It is supporting you so continuously that the support almost disappears from awareness. Your body presses downward. The surface presses upward. Nothing seems unusual, and yet this ordinary sensation leads directly into one of the deepest ideas in physics. If the floor beneath you could vanish without warning, you would not suddenly begin to feel a stronger pull of gravity. For a brief time, you would feel less. You and everything around you would begin falling together. A loose object beside you would seem to float. The familiar sensation of weight would disappear even though Earth's gravity would still be guiding your motion. Standing still is, in a strange sense, less natural than falling. That was one of the clues that led Albert Einstein toward a new description of gravity. But the story began much earlier, with falling stones, wandering planets, careful measurements, and a question that seems almost too simple to deserve a revolution. Why do things fall? Tonight, we will follow that question slowly. We will begin here, close to Earth, where gravity feels like the most obvious fact in the world. We will watch a thrown object curve back toward the ground, and then imagine throwing it so fast that the ground itself curves away beneath it. We will follow the moon around Earth, Earth around the sun, and the sun through the Milky Way. Then the picture will change. Gravity will stop looking like an invisible rope between masses and begin looking like geometry. Clocks will run at different rates. Light will bend. Stars will collapse. Black holes will form. Colliding neutron stars will make space-time itself tremble, and instruments on Earth will measure a change in length smaller than a proton. Farther out, gravity will gather matter into galaxies and clusters while the expansion of the universe pulls those structures apart from one another. And at the smallest imaginable scales, where quantum theory should meet curved space-time, the story will become uncertain again. Gravity is familiar enough to hold a cup on a table. It is mysterious enough that physics still does not possess a complete quantum theory of it. That combination makes gravity a good subject for a quiet night. The first important thing to notice is that gravity is not only something the Earth does. A book attracts the Earth. You attract the book. The moon attracts you. The chair attracts you. Two pebbles placed beside one another attract each other. The forces are usually far too small to notice because gravity between ordinary objects is extraordinarily weak, but the attraction is there. This universality was the great insight of Isaac Newton. By the 17th century, astronomers had already learned that the planets followed precise mathematical patterns. Johannes Kepler, working from the exceptionally careful observations of Tycho Brahe, had discovered that planets move around the sun in ellipses, not perfect circles. He found that a line from a planet to the sun sweeps out equal areas in equal times, so a planet moves faster when it is closer to the sun. He also found a relationship between orbital period and orbital size. Kepler's laws described what the planets did with remarkable accuracy. They did not explain why. On Earth, Galileo Galilei had been studying motion in a different way. He showed that falling bodies accelerate and that, when air resistance is removed, objects of different masses fall at the same rate. The famous story of Galileo dropping spheres from the Leaning Tower of Pisa may be partly legend, but his experiments with inclined planes and his analysis of falling motion were real and transformative. The old division between earthly motion and heavenly motion was weakening. Then Newton connected the two. In his Mathematical Principles of Natural Philosophy, published in 1687, Newton described a universal attraction between masses. The strength of that attraction increased with the masses involved and decreased with the square of the distance between them. Double the distance, and the gravitational attraction becomes 1/4 as strong. Triple the distance, and it becomes 1/9 as strong. This inverse square relationship turned out to be exactly the kind of law needed to explain Kepler's planetary motion. The famous apple story captures the conceptual leap even if its later retellings became polished. Newton himself recalled thinking about gravity after seeing an apple fall. The important question was not simply why the apple came down. People had watched objects fall for as long as people had existed. The deeper question was how far Earth's influence extended. Did the force that brought the apple downward stop at the top of a tree? Did it fade above the clouds? Or could it continue all the way to the moon? Suppose the moon were not held up by anything. It would fall toward Earth. But the moon also moves sideways very quickly. During the time it falls inward, it travels sideways, and Earth's curved surface falls away beneath it. The result is not a collision. It is an orbit. An orbit is a kind of continuous falling in which the falling object keeps missing the thing it is falling toward. Newton illustrated a related idea with an imaginary cannon on a very high mountain. Fire a cannonball slowly and it lands nearby. Fire it faster and it travels farther before hitting the ground. Fire it fast enough, in the idealized absence of air and mountains, and the curvature of Earth carries the surface away at the same rate that the cannonball falls. The cannonball never lands. It becomes a satellite. This is one of the most useful ways to understand orbital motion. The International Space Station is not beyond Earth's gravity. At its altitude, gravity is still most of the strength it has at the surface. Astronauts float because the station, the astronauts, and the objects inside it are all falling together around Earth. They are not in a place where gravity has disappeared. They are in free fall. The same idea explains why a spacecraft can coast around a planet without continuously firing its engines. Engines are needed to change the orbit, not to maintain an ideal orbit once established. The spacecraft's inertia carries it forward while gravity continually changes the direction of its motion. Closer to Earth's surface, we often describe gravity by an acceleration of about 9.8 meters per second squared. This means that, ignoring air resistance, the downward velocity of a freely falling object changes by about 9.8 meters per second each second near the surface. The number is not exactly the same everywhere. Earth rotates, and its rotation slightly reduces apparent weight most strongly near the equator. Earth is also not a perfect sphere. It bulges at the equator, so the equatorial surface is farther from the planet's center. Local geology matters too. Dense rock beneath one region can produce tiny differences in the local gravitational field. Those differences are small enough that daily life ignores them and precise enough that instruments can map them. Satellites have measured variations in Earth's gravitational field to track changes in groundwater, ice sheets, ocean mass, and the movement of material inside the planet. Gravity, because it responds to mass whether that mass is visible or hidden, becomes a way of weighing changes that cannot always be seen directly. Weight itself is worth separating from mass. Mass describes inertia and, in ordinary physics, the amount of matter involved. Weight is the force associated with a particular gravitational environment. Your mass would be nearly the same on Earth and on the Moon. Your weight would not. The Moon has about 1/6 of Earth's surface gravity, so a person who finds it difficult to lift an object on Earth could lift the same mass more easily on the lunar surface. The object would still resist changes in motion according to its mass. It would simply press downward less strongly. On Jupiter, there is no solid surface on which a person could stand in the ordinary sense, but near the level where atmospheric pressure resembles Earth's, gravitational acceleration is more than twice Earth's surface value. On Mars, it is a little over a third of Earth's. On a small asteroid, a gentle jump could send an astronaut surprisingly high. Gravity depends on mass and distance, not on how large an object looks. A neutron star can be only about the size of a city and possess more mass than the Sun. A diffuse cloud can be enormous and produce only a gentle local pull. To use Newton's law quantitatively, physics needs a constant called g, the Newtonian constant of gravitation. Its value is about 6.67430 times 10 to the minus 11 in the standard SI units. That very small number hints at gravity's weakness on laboratory scales. If you hold two 1 kilogram masses 1 meter apart, their mutual gravitational attraction is tiny. You do not see them slide toward one another because friction, vibration, air movement, electrical effects, and ordinary mechanical imperfections easily overwhelm the signal. This is why g has been surprisingly difficult to measure precisely. More than a century after Newton, Henry Cavendish performed an experiment so sensitive that it could measure the gravitational attraction between metal spheres inside a laboratory. The central device was a torsion balance. Imagine a light horizontal rod suspended from a thin wire, with small dense spheres attached near its ends. Larger spheres are brought nearby. Their gravitational attraction twists the suspended rod slightly. The wire resists the twist. By measuring the angle and knowing the properties of the apparatus, the tiny force can be inferred. Cavendish described his experiment in 1798 as a way of determining the density of Earth. In modern language, it effectively allowed g to be determined and therefore made it possible to calculate Earth's mass. For the first time, a laboratory experiment could weigh a planet. The measurement remains difficult today. The current recommended value of g is far less precise than constants, such as the speed of light. Different high-precision measurements have sometimes disagreed by more than their quoted uncertainties. Gravity becomes dominant in astronomy not because it is strong between individual particles, but because it has two special advantages. First, as far as ordinary matter is concerned, gravitational mass has one sign. There is no familiar negative gravitational mass that cancels positive mass on large scales the way positive and negative electric charges can cancel. Second, gravity reaches indefinitely far. The attraction weakens with distance, but it does not abruptly stop. A star contains an enormous amount of matter. A galaxy contains hundreds of billions of stars plus gas, dust, black holes, and a much larger reservoir of dark matter. Add enough mass over enough distance, and a force that is tiny between laboratory objects becomes the architect of cosmic structure. Even before reaching galaxies, gravity creates familiar patterns close to home. Consider the moon. The moon's gravity does not pull every part of Earth with exactly the same strength. The side of Earth closer to the moon feels a slightly stronger lunar pull than Earth's center. The far side feels a slightly weaker pull. This difference is a tidal force. Tides are not simply the moon lifting one ocean bulge on the side facing it. In a frame centered on Earth, the differential gravitational effect produces two broad tidal bulges, one roughly toward the moon and another roughly away from it. Earth's rotation carries coastlines through this pattern, although real tides are made much more complicated by ocean depth, basin shape, continents, resonances, winds, and the gravity of the sun. The sun also raises tides on Earth. When the sun, Earth, and moon are roughly aligned near new moon or full moon, lunar and solar tidal effects reinforce one another, producing spring tides with a larger range. Around first and third quarter moon, the effects partly oppose one another, producing neap tides. Tidal forces do more than move seawater. They slowly alter the Earth-Moon system itself. Earth rotates faster than the moon orbits. The tidal bulge raised on Earth is carried a little ahead of the line connecting Earth and moon. The moon's gravity pulls on that offset bulge, transferring angular momentum from Earth's rotation to the moon's orbit. Earth's day gradually lengthens. The moon gradually moves farther away, currently by a few centimeters per year, measured with lasers reflected from mirrors placed on the lunar surface by Apollo astronauts and Soviet robotic missions. The Moon, meanwhile, has already become tidally locked to Earth. It rotates once in approximately the same time it takes to orbit, which is why nearly the same lunar hemisphere always faces us. Tidal locking is not mysterious synchronization. It is the result of gravitational torques dissipating rotational energy over long periods. Across the solar system, tides can become far more dramatic. Jupiter's moon Io is squeezed and flexed as it moves through Jupiter's intense gravitational field, while orbital resonances with Europa and Ganymede keep Io's orbit slightly eccentric. The changing tidal distortion heats its interior. The result is the most volcanically active world known in the solar system. Saturn's moon Enceladus is also flexed by tides. Heat generated inside helps maintain a subsurface ocean beneath its icy crust, and jets of water-rich material erupt through fractures near its south pole. Move too close to a much denser object, and tides can become destructive. A small body approaching a planet can cross a distance known approximately as the Roche limit, inside which tidal forces can overwhelm the body's self-gravity and pull it apart, depending on its structure and rigidity. Near a black hole, the same principle can be extreme. The difference between the gravitational pull on one end of an object and the other can stretch it in one direction and compress it in others, an effect popularly called spaghettification. But there is a subtlety. For a small stellar mass black hole, tidal forces near the event horizon can be lethal. For a sufficiently massive supermassive black hole, the event horizon is so large that the curvature changes more gradually across the length of a human body. An infalling observer could cross the horizon without experiencing extraordinary tidal forces at that particular moment, although deeper inside the tidal forces would eventually grow devastating. Already, Newton's gravity has carried us from a falling object to planetary orbits, ocean tides, volcanic moons, and the destruction of stars. But Newton himself knew that his theory contained a strange feature. Gravity acted across empty space. The sun influenced Earth without a visible rope, fluid, or mechanical contact. Newton's mathematics predicted the motion magnificently, but the physical mechanism behind action at a distance remained obscure. There was another problem that would become more important 2 centuries later. In Newton's theory, changes in gravity were effectively instantaneous. If the sun could somehow move, the gravitational influence on Earth would change without delay. But special relativity, developed by Einstein in 1905, said that no physical influence could propagate faster than light. Something had to change. Einstein's route toward that change began with the simplest experience in our story: falling. Imagine a small windowless elevator drifting in empty space far from planets and stars. Inside it, you release a ball. The ball remains beside you. Now imagine instead that the elevator is falling freely toward Earth. Release the ball again. You and the elevator and the ball all accelerate together. For a sufficiently small laboratory and a sufficiently short time, the ball again appears to float beside you. Locally, free fall can erase the ordinary sensation of gravity. Now reverse the situation. Imagine the elevator in deep space being accelerated upward by a rocket. Release the ball. The floor rushes up to meet it. From inside the windowless elevator, the motion looks like the ball falling in a gravitational field. Einstein recognized a profound equivalence between acceleration and gravity. The idea did not mean that a gravitational field and acceleration are globally identical in every possible experiment. Tidal effects can reveal differences across a large enough region. Earth's gravitational field converges toward the planet and varies with position. A uniformly accelerating rocket can only imitate gravity locally. But locally, in a sufficiently small, freely falling laboratory, the ordinary effects of gravity can disappear. Einstein later called the insight that grew from this one of the happiest thoughts of his life. If gravity and acceleration were linked, then light should respond to gravity. Time should respond to gravity. The geometry used to describe space and time might itself have to become dynamical. Newton had described how masses move under gravity. Einstein began asking what gravity actually is. And the answer would eventually return us to the surface beneath you tonight, with a surprising conclusion. The feeling of weight is not the feeling of free fall. It is the feeling of being prevented from free fall. General relativity was completed in 1915 after years of difficult work. The mathematical language Einstein needed had been developed partly by mathematicians studying curved spaces for reasons that had little to do with astronomy. In ordinary Euclidean geometry, parallel lines remain parallel and the angles of a triangle add to 180 degrees. On a curved surface, those familiar rules can change. Imagine drawing a large triangle on Earth. Begin at the North Pole. Travel south along one line of longitude to the equator. Turn 90 degrees and travel a quarter of the way around the equator. Then turn 90 degrees again and travel north to the pole. The triangle has 3 right angles. Its angles add to 270 degrees. Nothing has gone wrong with geometry. The surface is curved. General relativity extends this idea far beyond the curvature of a 2-dimensional surface. Space and time form a 4-dimensional spacetime whose geometry can be curved by matter, energy, pressure, and momentum. The famous summary is often phrased this way: matter tells spacetime how to curve, and curved spacetime tells matter how to move. The phrase is memorable, but the underlying idea is more precise. In general relativity, freely moving objects follow geodesics, the closest equivalent to straight paths through curved spacetime. A planet orbiting the Sun is not, in this description, being continuously dragged sideways by an invisible Newtonian force in an otherwise passive space. It is following a geodesic through spacetime shaped by the Sun and by the rest of the universe. This does not make Newton wrong in ordinary situations. Newtonian gravity is an extraordinarily accurate approximation when gravitational fields are weak and velocities are much slower than light. Engineers can calculate most spacecraft trajectories using Newton's laws with suitable corrections. Bridges do not require Einstein's field equations. Baseballs do not need tensors to predict where they will land. A successful deeper theory does not usually erase the older one. It explains why the older one worked so well within a certain domain. Near very dense objects, at very high precision, or across cosmological distances, the differences become important. One of the first clues was Mercury. Mercury travels closest to the Sun and moves through a stronger gravitational field than the other planets. Its orbit is an ellipse, and the orientation of that ellipse slowly rotates. The point of closest approach to the Sun, called perihelion, advances from one orbit to the next. Most of this precession can be explained through the gravitational influence of the other planets and known Newtonian effects, but a small residual remained. For decades, astronomers could not fully account for an extra approximately 43 arcseconds of perihelion advance per century. Some proposed an unseen planet inside Mercury's orbit. It was even given a name, Vulcan. The planet was never found. When Einstein applied general relativity to Mercury, the unexplained precession emerged naturally from the curvature of spacetime near the Sun. No hidden planet was required. Einstein later recalled being overwhelmed by the success of the calculation. A discrepancy that looked tiny on the sky had become evidence that gravity was geometry. Another prediction involved light. If light follows the geometry of spacetime, then a ray passing near a massive object should be deflected. The Sun offered a test. During a total solar eclipse, the bright solar disk is covered by the Moon, making stars near the Sun's apparent position visible. If their light is bent while passing through the Sun's gravitational field, the stars should appear slightly shifted from their ordinary positions. Expeditions led by Arthur Eddington and Frank Dyson observed the eclipse of 1919 from Principe and Sobral. The historical story is often simplified into a perfect, decisive experiment in which Einstein defeated Newton overnight. The real measurements were difficult, affected by weather and instrument problems, and later historians have examined the uncertainties and data choices closely. But the broad result favored the larger deflection predicted by general relativity, and later radio and optical measurements confirmed gravitational light bending with vastly greater precision. Newspapers turned Einstein into an international celebrity. The universe had acquired a new geometry. Light bending has since become much more than a test of one theory. It is now a tool for seeing the invisible. Suppose a distant galaxy lies behind a massive cluster of galaxies. Light from the distant source travels along several possible curved paths through the spacetime surrounding the cluster. By the time those rays reach Earth, the background galaxy may appear stretched into an arc, duplicated into several images, or arranged into a nearly complete ring. When the alignment is especially symmetric, the result is called an Einstein ring. The foreground cluster acts like a lens. But unlike a glass lens, it is not refracting light through a material. It is bending the paths available to light through curved spacetime. The amount of distortion depends on the total mass along the line of sight. That includes matter that shines and matter that does not. This makes gravitational lensing one of the most important ways to map dark matter. A galaxy cluster may contain luminous stars and hot gas, but the lensing signal often reveals far more mass than the visible matter can provide. In some colliding clusters, the hot gas and the gravitationally inferred mass become spatially separated, offering especially powerful evidence that much of the mass is in a component that interacts differently from ordinary gas. Weak lensing is subtler. Most galaxies are not transformed into spectacular arcs. Their shapes are distorted by only a tiny amount. Any one galaxy already has an unknown intrinsic shape, so the lensing cannot be identified reliably from that object alone. But measure millions or billions of galaxies, and a statistical pattern appears. Their tiny correlated distortions reveal the distribution of foreground mass. Modern surveys use this cosmic shear to study how dark matter is distributed and how large-scale structure has grown over billions of years. ESA's Euclid mission is now mapping these distortions across an enormous region of the sky, using gravity itself as a probe of the dark universe. Lensing can also magnify distant objects. Galaxies too faint to study directly can become visible when a foreground cluster amplifies their light. A star on the far side of the observable universe can, for a time, be brightened enormously if it passes through a narrow caustic produced by the lensing geometry. Gravity becomes a natural telescope. The same curved spacetime that hides some things behind horizons can make other things easier to see. General relativity also changes time. Imagine two identical clocks. Place one at sea level and another on a mountain. After enough time, and with clocks precise enough, they will no longer agree. The higher clock runs slightly faster. This is gravitational time dilation. Closer to a massive body, deeper in a gravitational potential, less proper time passes between comparable events than it does higher up. The phrase, "time runs slower," can sound metaphorical. It is not. Atomic clocks measure it. Unstable particles experience it. Signals exchanged between different gravitational potentials reveal it. One of the classic early tests came in 1959 and 1960 at Harvard University, where Robert Pound and Glenn Rebka measured the change in energy of gamma rays traveling vertically through Earth's gravitational field. A photon climbing upward loses energy as measured by observers at different heights, corresponding to a tiny gravitational redshift. The experiment took place over a vertical distance of only about 22 meters. The effect was small. It was measurable. Today, optical atomic clocks are so sensitive that gravitational time dilation can be detected over height differences small enough to fit inside a laboratory. Move one clock upward, and its rate changes slightly. This has transformed relativity from an effect associated only with stars and black holes into something that precision metrology must consider across a building. There is a quiet consequence. Your head, when you are standing, ages very slightly faster than your feet because it is a little higher in Earth's gravitational field. The difference over a human lifetime is fantastically small, but it is real. The universe does not provide one single clock ticking identically everywhere. Time is local. Satellite navigation would fail quickly if this were ignored. GPS satellites orbit more than 20,000 kilometers above Earth. Their clocks are affected by two relativistic effects. Because the satellites move rapidly relative to clocks on Earth's surface, special relativity makes their clocks run slightly slower. Because the satellites are higher in Earth's gravitational field, general relativity makes their clocks run faster. The gravitational effect is larger. The net difference is about 38 microseconds per day. 38 millionths of a second sounds negligible. For a system that locates positions using signals traveling at the speed of light, it is enormous. If the relativistic corrections were not included, navigation errors would accumulate rapidly. Every time a phone uses satellite positioning, it quietly relies on Einstein. Gravity alters not only clock rates, but the frequency of light. A photon leaving a massive object is observed farther away at a lower frequency, shifted toward the red end of the spectrum. A photon falling inward is blue shifted. Near ordinary stars, the effect is modest. Near compact objects, it can become dramatic. The language of losing and gaining photon energy can be useful, but general relativity encourages care. Energy in curved spacetime does not always behave like a single globally conserved number in the way familiar from simple Newtonian problems. What is unambiguous is what local observers measure when they compare frequencies. This local nature of measurement appears throughout relativity. An observer falling freely past an event horizon and an observer hovering far away can assign very different coordinates and descriptions to the same process without disagreeing about any measurement they can physically compare. The geometry is not a stage on which physics happens. It participates. To understand what that means for ordinary weight, return to Earth. If you stand quietly on the floor, your path through spacetime is not a free fall geodesic. The material of Earth resists compression. Electromagnetic interactions between atoms in the ground and atoms in your feet produce an upward contact force. An accelerometer strapped to you reads approximately 1 g. If you jump from a sufficiently high platform and ignore air resistance, the accelerometer during free fall reads nearly 0. This is why astronauts aboard an orbiting spacecraft feel weightless while still deep within Earth's gravitational field. They are following geodesics. The support force has disappeared. What we casually call feeling gravity is mostly feeling non-gravitational forces preventing geodesic motion. This does not mean gravity is unreal. Tidal effects remain. Release two freely falling objects side by side above Earth, and their paths will slowly converge because both fall toward Earth's center. Release one above the other, and the lower one experiences slightly stronger gravity, so their separation changes. These relative accelerations between neighboring free fall paths are a direct manifestation of spacetime curvature. You cannot eliminate them everywhere merely by choosing a falling frame. This is why the image of a rubber sheet with a heavy ball making a dent is both helpful and misleading. It helps illustrate that geometry can guide motion, but it uses Earth's gravity to make smaller balls roll into a depression while supposedly explaining gravity itself. It also represents curved three-dimensional space as a curved two-dimensional surface embedded in another dimension, while general relativity concerns four-dimensional spacetime curvature that does not need to bend into an external space. The deeper mathematics is harder to picture. Fortunately, its predictions can be observed. One dramatic prediction is called frame dragging. A rotating mass does more than curve spacetime through its mass. It also drags the local geometry around with its rotation. Earth produces a tiny effect. Experiments including Gravity Probe B and analyses of laser-range satellites have measured this gravitomagnetic influence around our rotating planet. Near a rapidly spinning black hole, frame dragging becomes enormous. There, spacetime is not merely curved around the hole. It is twisted. Another prediction concerns the delay of light passing through a gravitational field. A radar signal sent past the Sun toward a planet and reflected back to Earth takes slightly longer than it would in flat spacetime. This Shapiro time delay, proposed by Erwin Shapiro in the 1960s, has been measured with radar echoes and spacecraft communications. Again and again, general relativity alters things that once seemed absolute. Distance, duration, the path of light, the orientation of a gyroscope, the orbit of a planet, all respond to geometry, and geometry responds to matter and energy. For most of the 20th century, these effects were tests of a beautiful theory. In the 21st, several have become routine tools. Gravitational lensing maps dark matter. Relativistic timing guides spacecraft. Pulsars test strong gravity. Black hole images test the environment just outside event horizons. Gravitational waves let us listen to moving spacetime itself. Before we reach those waves, it helps to ask where the great concentrations of gravity come from in the first place. Gravity does more than move objects after they exist. It builds them. Begin with a cold cloud in interstellar space. The cloud contains gas and dust spread across an enormous volume. Every particle attracts every other particle. Thermal motion, turbulence, magnetic fields, and pressure resist collapse. If a region becomes dense enough and cool enough that self-gravity wins, contraction begins. As the cloud shrinks, gravitational potential energy is converted into heat. Denser clumps form. Some fragment into multiple stars. At the center of a growing protostar, temperature and pressure rise until nuclear fusion can begin. A star is born because gravity compressed matter enough to ignite a process that then resists gravity for millions or billions of years. A main sequence star lives in a long negotiation. Gravity pulls inward. Pressure pushes outward. The pressure is supported by the energy generated through nuclear fusion in the core, along with the thermal motion and radiation associated with the star's hot interior. When the inward and outward influences balance, the star is in hydrostatic equilibrium. The Sun has maintained this approximate balance for about 4.6 billion years. Every second, fusion converts hydrogen into helium in the solar core. A small fraction of mass becomes energy. That energy works its way outward and eventually leaves as sunlight. Gravity made the core hot enough for fusion. Fusion prevents gravity from immediately compressing the Sun much further. The sunlight reaching Earth is therefore partly the consequence of a gravitational compromise inside a star. Stars also teach an important lesson about gravity. Gravity is patient. A single proton barely notices the gravitational attraction of another proton. But assemble roughly 10 to the 57th particles into a star, and the collective pull becomes capable of crushing matter toward extraordinary densities. The star's future depends strongly on mass. A relatively low-mass star like the Sun never becomes hot enough to fuse all the way to iron. Late in life, it expands into a red giant, loses its outer layers, and leaves behind a dense core called a white dwarf. A white dwarf no longer supports itself mainly through fusion. Instead, quantum mechanics enters. Electrons obey the Pauli exclusion principle. They cannot all occupy the same quantum state. Compress electrons into a smaller volume, and the available momentum states fill, producing electron degeneracy pressure. This quantum pressure can support a white dwarf against gravity, but only up to a limit. In the 1930s, Subrahmanyan Chandrasekhar showed that a white dwarf cannot remain stable above a mass of roughly 1.4 times the mass of the Sun, with the exact value depending on composition and other details. The result was initially controversial. It implied that sufficiently massive stellar cores could not simply stop collapsing as white dwarfs. Gravity had deeper destinations. Massive stars continue fusing heavier elements in successive stages until an iron-rich core develops. Fusion of iron does not release energy in the way fusion of lighter nuclei does. Once the core exceeds its ability to support itself, collapse can become catastrophic. Electrons and protons are driven together, producing neutrons and neutrinos. The core shrinks from thousands of kilometers across to a sphere only tens of kilometers wide. The outer star falls inward and is expelled in a core collapse supernova, assisted by a complex combination of neutrino heating, hydrodynamic instabilities, and the behavior of the collapsing core. What remains may be a neutron star. Or, if the collapsing core is massive enough, gravity may continue toward a black hole. A neutron star places ordinary intuition under extraordinary pressure. Imagine more mass than the Sun compressed into a sphere roughly 20 to 30 kilometers across. The average density approaches that of atomic nuclei. A cubic centimeter of neutron star matter would have an astonishing mass if somehow brought to Earth, though the popular image of scooping up a teaspoon is physically impossible because such material cannot remain in its neutron star state without immense pressure. At the surface, gravity is hundreds of billions of times stronger than Earth's. Escape speed is a large fraction of the speed of light. Spacetime is strongly curved. The matter inside is so dense that laboratories cannot reproduce it in bulk. Its exact equation of state, the relationship between pressure, density, temperature, and composition, remains uncertain. The core may contain mostly neutrons with smaller populations of protons and leptons. At greater densities, more exotic possibilities have been proposed, including hyperons or forms of deconfined quark matter. Observations can help decide. A softer equation of state allows a neutron star to compress more. A stiffer one produces a larger radius for a given mass. X-ray measurements from instruments such as NICE are constrained masses and radii. The existence of neutron stars around two solar masses already rules out some models that cannot support enough weight. And when two neutron stars spiral together, their shapes are distorted by each other's gravity. That tidal deformability leaves an imprint on the gravitational wave signal. A wave passing through Earth can therefore carry information about matter at densities beyond any terrestrial experiment. Gravity becomes a probe of the strong nuclear force. Many neutron stars also become pulsars. A newly formed neutron star can rotate rapidly and possess an intense magnetic field. Beams of electromagnetic radiation sweep through space from regions connected to the magnetic poles. If one beam crosses Earth, telescopes detect a pulse each rotation. Some pulsars rotate with extraordinary regularity. Millisecond pulsars can rival atomic clocks over long intervals. This regularity makes them exquisite laboratories for gravity. Place a pulsar in orbit around another compact object, and every pulse becomes a timing marker tracing the motion through curved spacetime. The most famous early example was the binary pulsar discovered by Russell Hulse and Joseph Taylor in 1974. Two neutron stars orbit each other. General relativity predicts that such a system should lose orbital energy by emitting gravitational radiation. As energy leaves, The orbit should shrink and the orbital period should change. Years of pulsar timing showed exactly this effect, matching Einstein's prediction with remarkable precision. Long before gravitational waves were detected directly, a pair of dead stars was quietly revealing that spacetime could carry energy away. The orbit was winding inward. Something invisible was leaving the system. It would take another 4 decades to measure those waves as they passed through Earth. Gravitational waves are not waves moving through spacetime in quite the same way that sound moves through air. They are waves of spacetime geometry itself. When a massive object accelerates, the gravitational field around it changes. In general relativity, those changes cannot be transmitted instantaneously. Disturbances propagate outward at the speed of light. Not every motion produces an appreciable wave. A perfectly spherical object expanding and contracting symmetrically does not radiate gravitational waves in the ordinary quadrupole description. A single spinning, perfectly symmetric sphere does not send out a changing gravitational pattern. What matters is a changing asymmetry in the distribution of mass. 2 compact objects orbiting one another provide an ideal source. Their changing quadrupole moment sends ripples outward. The system loses energy. The orbit slowly shrinks. The objects move faster. The gravitational waves become stronger and higher in frequency. The process accelerates until the 2 bodies merge. For black holes or neutron stars, the final seconds can release an astonishing amount of energy through a channel that is almost completely invisible to ordinary telescopes. Einstein himself doubted for a time whether gravitational waves would ever be measurable. Even after the mathematics was understood, the expected distortions reaching Earth seemed absurdly small. The experimental challenge can be appreciated with one number. A gravitational wave changes distances by a fractional amount called strain. For the first signal detected by LIGO, the strain was around 10 to the minus 21. Imagine a 4-kilometer ruler. A strain of that size changes its length by about 4 times 10 to the minus 18 meters. That is far smaller than a proton. The detector must distinguish this change from earthquakes, ocean waves, passing trucks, thermal vibrations, quantum fluctuations in laser light, tiny movements of mirrors, and countless other disturbances. The solution is an interferometer. LIGO uses 2 long perpendicular arms arranged in an L shape. A laser beam is split and sent down both arms, reflected by suspended mirrors, and returned. If the arm lengths remain exactly related, the returning light interferes in a predictable way. A passing gravitational wave stretches space in one direction while squeezing it in the perpendicular direction, then reverses the pattern. One arm becomes slightly longer while the other becomes slightly shorter. The difference changes the interference of the returning laser beams. This does not mean the mirrors are simply shaken by a conventional force. The geometry between freely suspended test masses is changing. LIGO has 2 widely separated detectors, one in Washington State and one in Louisiana. A genuine astrophysical wave should appear in both with a timing difference consistent with the travel time of light between the sites. On September 14, 2015, before the first observing run had formally begun, both detectors recorded a distinctive signal. It lasted only a fraction of a second in the most sensitive band. Its frequency and amplitude rose rapidly. Translated into audio frequencies, it made a short chirp. The waveform matched the final inspiral and merger of 2 black holes with masses of roughly 36 and 29 suns. The remnant contained about 62 solar masses. The missing mass had not disappeared. A few solar masses worth of energy had been carried away mainly as gravitational radiation. For a brief moment, the power emitted in gravitational waves exceeded the combined electromagnetic luminosity of the stars in the observable universe, even though almost none of that energy interacted strongly with matter on its journey. The source was around 1.3 billion light-years away. The waves had crossed cosmic distances, passing through stars, gas, dust, galaxies, and planets with almost no disturbance. Then, on Earth, they moved mirrors by less than the size of a proton. The detection was announced in February 2016. A century after Einstein predicted gravitational waves, humanity had measured them directly. The achievement opened a new kind of astronomy. Traditional telescopes collect electromagnetic radiation, radio waves, infrared, visible light, ultraviolet, X-rays, gamma rays. Neutrino observatories detect another messenger. Gravitational wave detectors listen to the dynamics of mass itself. Some of the objects they reveal are nearly dark. Two black holes can merge without producing a bright flash. Yet their changing geometry carries information about their masses, spins, orbital orientation, and distance. A new sky had become audible. Then, on August 17, 2017, the new method connected with nearly every older one. LIGO and Virgo detected a signal from two neutron stars spiraling together. The event became known as GW170817. About 1.7 seconds after the gravitational waves arrived, space telescopes detected a short gamma-ray burst from the same general region of sky. Astronomers around the world searched for the source. They found a fading optical and infrared transient in a galaxy about 130 million light-years away. For the first time, one cosmic collision had been studied through gravitational waves and across the electromagnetic spectrum. This was multi-messenger astronomy. The near-simultaneous arrival of gravitational waves and gamma rays, after traveling for around 130 million years, showed that gravitational waves propagate at essentially the speed of light to extraordinary precision. That one observation ruled out whole classes of modified gravity models in which the waves were expected to travel at a meaningfully different speed. The light from the merger also carried clues about the creation of heavy elements. When neutron-rich matter is ejected from a merger, nuclei can capture neutrons rapidly through the process. As unstable nuclei decay toward more stable forms, they release energy, producing a kilonova. Elements such as gold, platinum, and many others heavier than iron can be produced in such environments. Not every atom of gold in the universe must come from neutron-star mergers. Other rare astrophysical sites may contribute. But the 2017 event established these mergers as an important process factory. A wedding ring can contain atoms forged in a collision where gravity squeezed dead stars together. Gravitational wave astronomy continues to grow. Detectors have observed many binary black hole mergers, neutron star systems, and objects whose masses lie in intriguing transition regions. Each event expands a population rather than remaining one spectacular exception. The waveforms test general relativity in the strong field regime. They measure black hole masses that were difficult to discover electromagnetically. They help estimate cosmic expansion through a method called standard sirens, in which the amplitude and evolution of the gravitational waveform provide a direct distance scale. Future observatories will listen in different frequency bands. Ground-based detectors are best for relatively high-frequency waves from stellar mass compact objects. A planned space-based mission such as LISA will use laser-linked spacecraft separated by millions of kilometers, targeting lower frequencies from massive black hole mergers and compact binaries. At still lower frequencies, arrays of millisecond pulsars act as a detector on the scale of the galaxy. If a very long wavelength gravitational wave passes between Earth and a pulsar, it changes the arrival time of the pulses slightly. By monitoring many pulsars for years, astronomers can search for a correlated pattern across the sky. Recent pulsar timing results have found evidence for a nanohertz gravitational wave background. Populations of supermassive black hole binaries are a leading explanation, although the exact astrophysical origin and detailed spectrum remain active areas of research. Gravity can therefore be heard across an enormous range of timescales, a fraction of a second chirp from stellar black holes, minutes or hours in a future space detector, years-long patterns in pulsar timing. The same theory connects them. The black holes producing many of these signals deserve a slower look. A black hole is not simply an object with very strong gravity in the ordinary sense. It is a region of space-time containing an event horizon, a boundary beyond which future directed paths cannot return to the outside universe. The simplest ideal black hole is described by the Schwarzschild solution, found by Carl Schwarzschild soon after Einstein completed general relativity. Schwarzschild was serving in the German army during the First World War when he derived the solution. He died in 1916, only months later. The mathematics he produced described spacetime outside a perfectly spherical, non-rotating mass. Within it appears a characteristic radius. For a mass equal to the Sun, the Schwarzschild radius is about 3 kilometers. For Earth, it is about 9 millimeters. This does not mean there is a tiny black hole hidden inside Earth. Earth's actual radius is about 6,371 kilometers, enormously larger than its Schwarzschild radius. To make a black hole from Earth's mass, that mass would need to be compressed inside a region only millimeters in scale. For an ordinary human body, the corresponding radius is unimaginably smaller than an atomic nucleus. Black holes form naturally because stellar collapse can compress large masses far enough that no known pressure can stop the collapse before an event horizon forms. The event horizon is not a solid shell. An astronaut falling through the horizon of a sufficiently large black hole would not strike a surface. There need not be a local flash, barrier, or sudden mechanical event marking the crossing. The horizon is defined globally by which paths can still reach distant observers and which cannot. This makes it profoundly different from the surface of a star. To an observer far away, signals from an infalling object become increasingly redshifted and delayed. The object appears to fade as its light loses energy and takes longer to arrive in the chosen coordinates. To the falling observer, their own proper time continues normally. They cross the horizon after a finite interval. These descriptions are not contradictions. They arise because time and simultaneity behave differently in curved spacetime. Once inside a classical black hole horizon, all future directed paths lead deeper inward. People sometimes say that the singularity lies at the center in the same ordinary way that Earth's center lies beneath its surface. For a static Schwarzschild black hole, that picture is incomplete. Inside the horizon, the mathematical roles of radial and temporal directions change in a way that makes decreasing radius unavoidable, rather like moving toward the future is unavoidable outside. The classical singularity is not merely a dangerous point that one could steer around. It is the end of future directed time-like paths in the idealized solution. But the word singularity is also a warning label on the theory. General relativity predicts that curvature becomes unbounded and the classical description becomes incomplete. Most physicists do not interpret this as proof that nature literally contains an infinitely dense point described exactly by classical equations. It is evidence that a deeper theory, presumably involving quantum gravity, is needed. Real astrophysical black holes also rotate. A rotating black hole is described by the Kerr solution. Rotation changes the geometry dramatically. Outside the event horizon lies an ergosphere where space-time is dragged so strongly that no object can remain stationary relative to distant stars. Everything must co-rotate to some degree. In principle, rotational energy can be extracted from a spinning black hole. Astrophysical magnetic fields and plasma around rotating black holes can tap spin energy through mechanisms related to the geometry and power enormous jets extending far beyond their host galaxies. The black hole itself does not shine. Its surroundings can be among the brightest objects in the universe. Gas falling toward a black hole usually carries angular momentum, so it does not plunge straight inward. It forms an accretion disk. Different parts of the disk orbit at different speeds. Turbulence and magnetic stresses transfer angular momentum outward, allowing matter to spiral inward. Gravitational potential energy becomes heat. The inner disk can reach millions of degrees and emit intense X-rays. Around supermassive black holes feeding rapidly in young galaxies, accretion can power quasars bright enough to outshine all the stars in the host galaxy. The darkness of the hole creates a luminous environment. In 2019, the Event Horizon Telescope collaboration released the first image of the shadow around a black hole. The target was M87 star, the supermassive black hole at the center of the galaxy Messier 87. About 54 million light-years away and billions of times more massive than the Sun. The image did not photograph the black hole as a dark sphere with a visible surface. It mapped radio emission from hot plasma on scales comparable to the event horizon. Strong gravitational lensing creates a bright ring-like structure around a dark central shadow, whose apparent size is larger than the event horizon itself. The observation required radio telescopes across Earth to work together through very long baseline interferometry, creating the resolving power of a virtual Earth-sized telescope. In 2022, the collaboration released the first image of Sagittarius A star, the black hole at the center of our own Milky Way. Sagittarius A star is much closer than M87 star, only about 26,000 light-years away, but it is far less massive. That makes the gas around it change on much shorter timescales, complicating the reconstruction. During the hours of observation, the source itself can vary significantly. The two black holes differ in mass by more than 3 orders of magnitude, yet their observed ring scales are consistent with the predictions of general relativity. Gravity keeps using the same geometry across enormous differences in size. Black holes also produce some of the strongest examples of gravitational time dilation. Imagine hovering outside a black hole using a powerful rocket. The closer you remain to the horizon of a non-rotating black hole, the more acceleration is required to avoid falling. Signals sent outward from you become increasingly redshifted. Compared with distant clocks, your clock appears to run increasingly slowly. A freely falling observer experiences something different because free fall removes the local support force. Near a large horizon, the crossing itself can be uneventful. Again, the distinction between hovering and falling matters. One path resists gravity, the other follows spacetime. Tidal forces return too. For a stellar mass black hole, the change in gravity across a human body becomes huge before or near the horizon. The body is stretched radially and compressed sideways. For a supermassive black hole, the horizon can be crossed while local tidal forces remain modest, because the characteristic curvature at the horizon decreases as black hole mass increases. The danger has not vanished. It has moved deeper inside. Black holes are dark in classical general relativity. Quantum field theory changes that. In 1974, Stephen Hawking showed that quantum fields around an event horizon cause a black hole to emit thermal radiation. The popular story describes pairs of virtual particles appearing beside the horizon, one falling inward and the other escaping. That picture can be a rough mnemonic, but it is not the actual derivation and can create confusion about what virtual particles are. A more accurate statement is that the definition of a particle depends on the spacetime and on the observer. Quantum fields that begin in a state interpreted as vacuum before black hole formation can later be observed at infinity as containing a thermal flux of particles. The horizon changes the relationship between field modes. The result is Hawking radiation. A black hole therefore has a temperature. The larger the black hole, the lower the temperature. A stellar mass black hole is far colder than the cosmic microwave background today, so it absorbs more ambient radiation than it emits through Hawking's effect. An isolated black hole in a far colder future universe would gradually lose mass. As it shrinks, it becomes hotter and radiates faster. For a black hole with roughly the mass of the Sun, the evaporation time is on the order of 10 to the 67th years, depending on the exact assumptions in mass. That number is almost meaningless on human timescales. The universe is only about 13.8 billion years old. Hawking evaporation of stellar black holes belongs to an unimaginably distant cosmic future. Yet the calculation connected three theories that normally live in different worlds: general relativity, quantum field theory, thermodynamics. Black holes were assigned temperature and entropy. The entropy of a black hole is proportional not to its volume, but to the area of its event horizon, measured in tiny Planck scale units. That area law became one of the deepest clues in theoretical physics. It suggested that the amount of information associated with a region might somehow be encoded on a boundary. Ideas inspired by black hole thermodynamics contributed to the holographic principle and to developments in string theory, quantum information, and the search for quantum gravity. They also produced a paradox. Suppose a book falls into a black hole. Not merely the ink and paper, but the exact quantum state of all its particles carries information. In ordinary quantum mechanics, information is not expected to be fundamentally destroyed by unitary evolution. But Hawking's original calculation made the outgoing thermal radiation appear almost featureless, depending only on broad black hole properties. If the black hole evaporates completely and the radiation contains no record of what fell in, information seems lost. General relativity and quantum mechanics appear to demand incompatible answers. This is the black hole information paradox. For decades, it has forced physicists to examine what an event horizon, entropy, locality, and even spacetime itself mean. Many modern approaches strongly suggest that information is preserved, and developments involving holography and calculations of black hole entropy have sharpened that view. But a fully settled microscopic account applicable to realistic evaporating black holes remains part of the larger unfinished problem of quantum gravity. Black holes are therefore more than collapsed stars. They are laboratories we cannot enter and report back from, but whose existence turns abstract conflicts between our best theories into physical questions. A falling stone led Newton to universal gravitation. A falling elevator led Einstein toward curved spacetime. A collapsing star leads physics to a horizon where spacetime, quantum theory, and information all meet. And from there, the question expands again. Black holes are extreme, but gravity shapes the universe even where no horizon exists. It gathers matter slowly, almost invisibly, across millions and billions of years. To understand the largest structures in existence, we have to move from collapse to construction. Long before there were planets, oceans, trees, or people, gravity was already working. The early universe was hot, dense, and remarkably uniform. The cosmic microwave background shows us matter and radiation when the universe was about 380,000 years old. Across the sky, its temperature differs only by tiny fractions. Those tiny differences mattered. Some regions contained slightly more matter than average. Gravity amplified the imbalance. A region that was a little denser exerted a little more gravitational pull. More matter moved toward it. The region became denser still. Over enormous spans of time, small primordial fluctuations grew into a cosmic network of galaxies, groups, clusters, filaments, and vast underdense voids. The night sky looks scattered with separate islands of light. On larger scales, those islands form structure. Galaxies gather in groups. Groups gather into clusters. Clusters connect along filaments that stretch for hundreds of millions of light years. Between them lie enormous voids containing far less matter. Computer simulations of cosmic structure begin with an early universe whose initial fluctuations are constrained by observations. Apply gravity, cosmic expansion, ordinary gas physics, star formation, and feedback, and a web-like structure emerges that resembles the universe mapped by galaxy surveys. But there is a crucial ingredient. Visible matter alone does not appear to provide enough gravitational influence. The evidence for unseen mass accumulated from several directions. In the 1930s, Fritz Zwicky studied galaxies in the Coma cluster. Their velocities seemed too large for the visible mass of the cluster to keep them bound. He inferred the presence of missing mass. Decades later, measurements of spiral galaxies strengthened the problem. If most of a galaxy's mass were concentrated where most of its starlight is seen, stars far from the center should orbit more slowly with increasing distance in a broadly Keplerian way. Instead, many galaxy rotation curves remain approximately flat far beyond the bright central regions. Something supplies additional gravity. Vera Rubin, Kent Ford, and others produced influential measurements showing how widespread this behavior is. The simplest successful cosmological picture includes dark matter, matter that contributes gravity but does not emit, absorb, or scatter light strongly enough to have been detected directly through ordinary electromagnetic methods. Dark matter is not proposed merely because one set of stars moves unexpectedly. It helps explain gravitational lensing, galaxy clusters, the pattern of fluctuations in the cosmic microwave background, the formation of large-scale structure, and other observations within one framework. We still do not know what dark matter is made of. It may consist of a new kind of particle. Many candidates have been proposed, from weakly interacting massive particles to axion-like particles and other possibilities. Searches in underground detectors, accelerators, astrophysical observations, and precision experiments continue. It is also reasonable to test whether our theory of gravity could be incomplete on galactic or cosmological scales. Modified gravity ideas can reproduce some phenomena, particularly regularities in galaxy dynamics, but matching the full range of cosmological evidence is demanding. Science does not decide the question by loyalty to one category. It asks which model explains the most observations with the fewest unresolved contradictions. At present, cold dark matter remains central to the standard cosmological model, even though its microscopic identity is unknown. Gravity therefore shapes galaxies partly through something we have not yet identified. There is another invisible component whose role is almost the opposite. In the late 20th century, astronomers used distant type 1a supernovae to measure the history of cosmic expansion. They expected the attraction of matter to slow the expansion over time. Instead, the observations indicated that expansion has been accelerating during the more recent history of the universe. Within general relativity, this behavior can be described by a component with sufficiently negative pressure, commonly called dark energy. The simplest version is Einstein's cosmological constant, an energy density associated with empty space that remains constant as the universe expands. The name dark energy does not identify a substance whose nature is understood. It labels a phenomenon encoded in cosmological models. Observations suggest that dark energy is currently the dominant contribution to the universe's total energy density. Its gravitational effect on cosmic expansion is unlike the familiar attraction of ordinary matter. General relativity permits pressure as well as energy density to influence spacetime curvature. A component with negative enough pressure can drive accelerated expansion. This does not make local gravity disappear. The solar system remains bound. The Milky Way remains bound. The local group remains bound. On small scales, gravitationally bound systems are not carried apart simply because cosmic expansion is accelerating. Expansion is a property of the large-scale space-time, not an explosion pushing every object away from every other object like debris. A useful distinction is between systems participating in the Hubble flow and systems whose internal binding overwhelms that expansion. Your body does not expand with the universe. Neither does Earth. Neither does the solar system. Even the Milky Way and Andromeda are moving toward one another, but recent simulations based on improved Hubble and Gaia measurements show that a direct collision is no longer considered certain. Their future depends sensitively on the motions of the local group. What remains clear is that cosmic expansion does not simply pull the two galaxies apart at their present separation. On sufficiently large scales, however, galaxies not gravitationally bound to us recede as space evolves. Gravity and expansion compete in shaping cosmic history. The mathematical framework comes from applying general relativity to a universe that is homogeneous and isotropic on large scales. The resulting Friedmann equations connect the expansion rate with matter, radiation, spatial curvature, and dark energy. These equations tell a story of changing dominance. In the very early hot universe, radiation was dynamically important. Later, matter dominated the expansion and provided the gravitational scaffolding for structure growth. More recently, dark energy became dominant in the expansion budget and structure growth began to slow relative to what it would be in a matter-only universe. Observational cosmology now tests gravity not only near the sun or a black hole, but across billions of light years. Measure how galaxies cluster. Measure how lensing maps matter. Measure how expansion changes with time. Measure how fast cosmic structure grows. Together, these observations ask whether general relativity still works on the largest accessible scales. So far, it remains extraordinarily successful, but the unknown nature of dark matter and dark energy keeps the story open. Gravity also determines possible futures for the universe. Older popular accounts often described three simple options. Enough matter would halt expansion and cause a big crunch. Less matter would allow expansion forever. Exactly the critical amount would produce a boundary case. Dark energy made the picture more complicated. The fate of the universe depends not only on matter density and spatial curvature, but on the properties of dark energy. If dark energy behaves like a cosmological constant, expansion continues accelerating indefinitely. Galaxies outside our gravitationally bound neighborhood eventually recede beyond our observable horizon. Stars fade. Stellar remnants remain. Black holes dominate increasingly empty regions and, on vastly longer timescales, may evaporate through Hawking radiation. The universe approaches a cold, dilute state sometimes described as heat death. If dark energy changes with time, other possibilities exist. A hypothetical form whose density increases as the universe expands could eventually produce a big rip, overcoming progressively smaller bound systems. Other models allow dark energy to decay or change sign, potentially altering the future dramatically. A cosmological constant remains the simplest benchmark and still fits much of the evidence. But recent DESI results, when combined with other cosmological observations, have strengthened hints that dark energy may evolve with time. The evidence is not yet decisive, and the completed DESI survey is intended to test that possibility with greater precision. Gravity gives us equations for these futures. Observation decides which terms nature has chosen. The large-scale story also reveals why saying gravity is the weakest force requires context. At the level of elementary particles, gravitational interactions are fantastically weaker than electromagnetism or the nuclear forces. A simple refrigerator magnet can lift a paper clip against the gravitational attraction of the entire Earth. But the magnet works because electromagnetic charges can arrange themselves into structures with strong local fields. On cosmic scales, positive and negative electric charges tend to neutralize each other. Large objects are usually close to electrically neutral overall. Gravity does not neutralize in the same ordinary way. Every contribution of positive mass energy adds to the attraction or, more generally, to spacetime curvature. So gravity wins not by being strong per particle, but by adding coherently across enormous amounts of matter and by reaching across unlimited distances. This is why gravity is almost irrelevant to the structure of an atom and decisive for the structure of a galaxy. Inside an atom, electromagnetism controls electrons. Inside a nucleus, the strong interaction binds protons and neutrons. Across a planet, star, galaxy, or cluster, gravity takes over. The hierarchy of scales is part of the beauty. Different laws become dominant at different levels without ceasing to exist. Yet when physics tries to push gravity down toward the smallest possible scales, a serious problem appears. General relativity is a classical theory. Quantum mechanics and quantum field theory describe matter and the other known fundamental interactions. Both frameworks have been tested with extraordinary precision. They do not fit together straightforwardly in the most extreme situations. This does not usually matter when calculating the orbit of Earth. Quantum corrections to solar system gravity are absurdly tiny. It does not matter when calculating the spectrum of hydrogen to ordinary precision. Space-time curvature across an atom is negligible. The conflict becomes unavoidable where enormous energy is compressed into tiny regions. The earliest moments of the universe. The interior or endpoint of black hole collapse. Distances approaching the Planck scale. A naive attempt to quantize general relativity in the same perturbative way used successfully for electromagnetism produces divergences that cannot all be absorbed into a finite set of measurable parameters. General relativity can still be treated as an effective quantum field theory at low energies, where it gives sensible quantum corrections. The problem is ultraviolet completion. What fundamental theory describes gravity when energies become so high that the smooth classical picture of spacetime itself may fail? One way to express the scale is through Planck units, built from the gravitational constant g, the speed of light, and Planck's constant. The Planck length is about 1.6 times 10 to the minus 35 meters. This number is not necessarily the size of the smallest literal pixel of space. Physics does not know that space is discretized into Planck-length blocks. Instead, the Planck scale marks the regime where dimensional arguments suggest quantum gravitational effects should become impossible to ignore. It is extraordinarily remote from direct laboratory access. The Large Hadron Collider probes distances many orders of magnitude larger. A direct experiment at the Planck energy would require conditions far beyond any conceivable accelerator built with current technology. This enormous separation helps explain why quantum gravity is so difficult. The theory becomes essential where experiments are hardest. Several research programs attempt to bridge the gap. String theory replaces fundamental point-like particles with one-dimensional extended objects called strings. Different vibrational modes correspond to different particles. One mode naturally behaves like a massless spin 2 particle with the properties expected of a graviton, so gravity arises within the framework rather than being added separately. String theory also connects gravity with gauge interactions and has produced deep mathematical insights, including powerful examples of holographic duality. But realistic formulations involve additional structure, such as extra spatial dimensions, and the landscape of possible solutions is enormous. No unique experimentally confirmed version has yet emerged as the description of our universe. Loop quantum gravity begins from a different direction. Rather than placing strings in a quantum framework, it tries to quantize the geometry of spacetime itself. In the resulting mathematical description, quantities associated with area and volume can have discrete spectra. Spin networks and related structures describe quantum geometry. The approach has generated models of black hole entropy and early universe cosmology, including scenarios in which a classical Big Bang singularity is replaced by a quantum bounce. But again, no decisive experimental observation has selected the theory. Other approaches include asymptotic safety, causal dynamical triangulations, group field theory, causal sets, emergent gravity ideas, and more. The variety is not a sign that physics has learned nothing. It reflects the difficulty of a problem with limited direct experimental guidance. Each approach tries to preserve the established successes of general relativity and quantum mechanics while changing something deep enough to make them compatible. A hypothetical quantum of the gravitational field is called the graviton. In a weak field quantum description, one expects it to be massless and to carry spin too. Gravitons are useful in theoretical calculations. No individual graviton has ever been detected. There are strong arguments that detecting a single graviton may be effectively impossible with any realistic apparatus because gravitational coupling is so weak. A detector sensitive enough to absorb individual gravitons would face extraordinary physical constraints and background problems. This is an unusual situation. Photons can be counted. Electrons can be isolated. Individual neutrinos are difficult but detectable. Gravity's hypothetical quantum may remain inaccessible one particle at a time. That does not make quantum gravity untestable in principle. Nature may amplify quantum gravity effects through the early universe, black holes, precision interferometry, or subtle departures from expected behavior. The challenge is finding a prediction that is both distinctive and observable. The early universe is especially tempting because every observable region was once compressed into a far denser state. Quantum fluctuations during an inflationary phase may have been stretched to cosmic scales, eventually seeding the structure's gravity later amplified. The pattern in the cosmic microwave background already contains information about primordial fluctuations. A detection of primordial gravitational waves through a characteristic polarization pattern could provide information about extremely high energy physics, although such a signal has not yet been established. Black holes offer another route because horizon thermodynamics seems to demand a microscopic quantum description. The entropy area relation says a black hole of a given horizon area has an enormous but finite entropy. What microscopic states does that entropy count? String theory has answered this for certain idealized black holes. Other approaches produce their own state counting results. But a universal account connecting realistic astrophysical holes, formation, evaporation, information, and interior geometry remains unfinished. There is a possibility even more radical than quantizing an already existing spacetime. Spacetime itself may be emergent. In some modern approaches, geometry appears to be connected to quantum entanglement and information in a deeper underlying system. The idea is not established fact, and the precise meaning varies between theories. But it reverses the usual hierarchy. Instead of quantum fields living in spacetime, spacetime might arise from quantum relationships. Gravity, in that picture, would not be one more force placed beside electromagnetism. It could be a large-scale manifestation of deeper quantum structure. This brings us to the farthest conceptual edge of a story that began with weight. The floor beneath you feels solid. The planet beneath the floor feels massive. Newton says the masses attract. Einstein says your freely falling path belongs to curved spacetime. Quantum gravity may eventually say that even spacetime is not fundamental. We do not yet know. It is important to allow that uncertainty to remain. Physics has a complete, highly tested description of gravity across an enormous range of observed phenomena in general relativity. It does not have a confirmed quantum theory of gravity. The lack of a final theory does not erase what is known. It identifies the boundary, and science often advances by learning where a successful description stops. From that distant theoretical edge, the scale can begin to shrink again, toward the gravity a human body actually lives inside. We are adapted to live under almost exactly one Earth gravity. Our bones, muscles, circulation, balance organs, and development evolved in that environment. When humans leave it, biology changes. Astronauts in orbit are in continuous free fall, and the absence of ordinary weight bearing changes the body. Bones lose mineral. Muscles that normally oppose gravity weaken. Fluids shift toward the upper body. The vestibular system must reinterpret signals because the familiar distinction between up and down no longer matches the body's acceleration. The cardiovascular system adapts to a world where blood does not pool in the legs in the usual way. Exercise and other countermeasures reduce some of these changes, but long-duration spaceflight remains a biological experiment in what happens when an organism built by Earth is removed from Earth's support forces. Artificial gravity through rotation is one proposed solution for long missions. Rotate a habitat and occupants are pressed toward the outer wall. In the rotating frame, the effect can imitate some aspects of gravity, though Coriolis forces and changing acceleration across the body can make small rotating habitats uncomfortable. There is a nice symmetry here. Einstein used acceleration to understand gravity. Spacecraft designers may use acceleration to reproduce the biological effects of gravity. Even on Earth, organisms reveal gravity's influence. Plant roots generally grow in directions shaped partly by gravitropism. Specialized dense particles within certain cells settle under gravity and help guide growth responses. Stems often grow against the gravitational direction while roots grow with it, interacting with light, water, touch, and chemical signals. Animals rely on gravity to orient bodies, build skeletons, circulate fluids, and move. A whale is supported by buoyant water in a way an elephant is not. A tree must raise water and support tissue against gravity for decades or centuries. The maximum sizes and shapes available to living organisms are partly constrained by the constant downward environment in which they evolved. Gravity is weak at the scale of molecules. Life, by becoming large, has to negotiate with it. The architecture of bones is a response. The trunk of a tree is a response. The arch of a foot is a response. The pressure gradient in a standing human bloodstream is a response. The science of gravity is therefore not confined to astronomy. It is built into posture. And because gravity changes with altitude, latitude, geology, and planetary mass, it also becomes a tool. Geophysicists measure tiny changes in gravitational acceleration to infer hidden structures underground. A dense body can create a small positive gravity anomaly. A buried cavity can create a negative one. Volcanoes can be monitored as magma moves. Groundwater loss changes mass distribution. Ice sheets losing billions of tons alter Earth's gravitational field. Space missions designed to measure gravity with extreme precision have watched water and ice move around the planet. Gravity does not care whether mass is visible. A satellite can feel a drought, not because it detects dry soil directly, but because missing water means missing mass. The orbit changes by a tiny measurable amount. What began as the science of falling becomes a way of watching Earth's climate system. and still the surface beneath you remains steady. Earth's mass is about 6 times 10 to the 24 kilograms. You contribute to Earth's gravitational field too, but by an amount so small that it is irrelevant to planetary motion. The Earth pulls you downward. You pull Earth upward with exactly the same Newtonian force. Because Earth has an enormous mass, its resulting acceleration toward you is imperceptibly small. The symmetry can feel strange. When you drop a ball, the ball falls toward Earth. Earth also moves toward the ball. The center of mass of the two-body system behaves consistently, even though one motion is obvious and the other is not. The same principle scales upward. Earth and the Moon both orbit their common center of mass, called the barycenter. That point lies inside Earth, but not at Earth's exact center. The Sun and Jupiter orbit a common barycenter that can lie near or even outside the solar surface, depending on the configuration of the planets. Stars with planets wobble around system barycenters. Astronomers detect some exoplanets by measuring that stellar reflex motion. Gravity reveals unseen worlds through the movement of their stars. It also reveals unseen companions through timing. A pulsar's pulses arrive early and late as the star moves around a barycenter with an orbiting object. Binary stars shift their spectral lines as they alternately approach and recede. Again, the method is indirect. We infer an invisible thing because gravity makes something visible move. This may be gravity's most characteristic signature. It is often known through consequences: a curve in a trajectory, a delay in a clock, a stretched image, a chirp in an interferometer, a star moving too quickly, a galaxy bending light more strongly than luminous matter can explain. Gravity itself has no color, but it rearranges the universe into patterns we can see. Once we are back near Earth, one old Newtonian thought experiment reveals how unintuitive even familiar gravity can be. Imagine a perfectly straight tunnel drilled through Earth from one side to the other, passing exactly through the center. Ignore the obvious engineering impossibilities: immense pressure, molten and plastic rock, extreme temperature, air resistance, Earth's rotation, and the fact that a real tunnel could not remain open. Treat Earth for a moment as a perfectly spherical body with a simple density structure. What would happen if you stepped into the tunnel? At the surface, gravity accelerates you inward. As you fall deeper, something changes. There is now some Earth above you as well as below you. Does that material above pull you backward strongly enough to cancel the planet beneath? Newton's shell theorem gives a beautiful answer. A uniform spherical shell of matter produces no net gravitational force on a point located anywhere inside the shell. Every nearby patch of the shell pulls more strongly because it is closer, but a larger amount of more distant material lies in the opposite direction. The geometry makes the contributions cancel exactly. This means that, at any depth inside an ideal spherical Earth, only the mass at smaller radii contributes to the net inward gravitational pull. The layers outside your current radius cancel as complete shells. As you approach the center, less enclosed mass remains beneath your effective radius. For a uniform density Earth, the gravitational force would decrease approximately in proportion to your distance from the center. At the exact center, symmetry becomes complete. Every direction contains equal mass. The net gravitational force is zero. You would be weightless there, not because Earth had stopped containing 6 times 10 to the 24 kilograms of mass, but because all directions pull equally. If the tunnel were a perfect vacuum and Earth were uniform and non-rotating, you would not stop permanently at the center. You would have acquired speed during the fall. You would pass through, slow as you climbed toward the opposite surface, momentarily reach zero speed there, and then fall back again. The motion would resemble a giant oscillator through the planet. For a uniform density sphere, the trip from one surface to the other would take on the order of tens of minutes. A more realistic Earth density profile, changes the exact time, and rotation complicates the trajectory, but the thought experiment remains instructive. Gravity at Earth's surface is not simply all the planet pulling downward from below. It is the vector sum of contributions from the whole mass distribution. Symmetry can make an enormous amount of surrounding matter produce zero net force. The same shell theorem explains another useful fact. Outside a perfectly spherical mass distribution, gravity behaves as though all the mass were concentrated at the center. That is why Newton could model Earth and the Sun as point masses when calculating distant orbits, despite their enormous physical sizes. A complicated extended body becomes simple when spherical symmetry is good enough. Inside, however, the story changes. This is a recurring theme in gravity, where the masses matters. Rearrange the same total mass and the gravitational field can change. Compress a star and surface gravity increases. Spread matter into a diffuse cloud and local gravity weakens. Move groundwater underground and satellites can detect a tiny shift. Place mass in a ring, sphere, disk, or filament, and each geometry creates a different field. General relativity deepens the statement by allowing not only mass but energy, momentum, pressure, and stress to influence spacetime curvature. Gravity is universal, but it is not indifferent to structure. Even weightlessness has several meanings. At Earth's center, idealized weightlessness comes from symmetry, poles cancel. In orbit, weightlessness comes from free fall. Spacecraft and astronaut accelerate together. Far from major masses, weightlessness can mean the gravitational field is simply very weak. These situations can feel similar to a person carrying an accelerometer, yet arise from different geometries. The distinction is useful because gravity is rarely understood by sensation alone. A person can feel weightless where Earth's gravity is strong. A person can feel heavy in a rocket far from any planet if the rocket accelerates. A scale measures support force, not the gravitational field directly. Once that distinction is clear, even an ordinary bathroom scale becomes more interesting. The ground under you is only one location inside a much larger gravitational structure, near the surface of a nearly spherical rotating planet whose field reaches far beyond the moon. And the number your bathroom scale displays is not a direct meter of some invisible fluid called gravity. It measures how strongly the surface must support you to keep you from following the motion you would otherwise take. There is one more way to make gravity visible. Remove it from the picture. Imagine Earth with the same atoms, oceans, atmosphere, and sunlight, but no gravitational attraction. There could be no ordinary Earth. The atmosphere would not remain wrapped around the planet. Oceans would not remain in their basins. Loose rock and dust would not be held to a surface. The pressure inside the planet would vanish. The sun itself could not exist in its present form because the gas from which it formed would never have collapsed, and its core would not be compressed enough for sustained fusion. The solar system is not a collection of finished objects later arranged by gravity. Gravity participated in making the objects. About 4.6 billion years ago, the solar system formed from a collapsing region of a molecular cloud. As material contracted, conservation of angular momentum helped the cloud flatten into a rotating disk around the young sun. Dust grains collided and stuck. Larger aggregates developed. Planetesimals formed. Once bodies became sufficiently massive, gravity increased their ability to collect surrounding material. Growth could accelerate. Embryonic planets collided, scattered one another, and reshaped the disk. The current solar system preserves traces of that violent construction. Earth's layered interior also reflects gravity. When the young planet was hot enough for substantial melting and rearrangement, dense iron-rich material sank toward the center while lighter silicate material remained above it. This differentiation released gravitational energy as heat. Gravity helped build the core, mantle, and crust. It continues to compress the planet today. Pressure rises with depth because deeper material supports the weight of everything above it. At Earth's center, pressure is millions of times atmospheric pressure. The planet is not held together by gravity alone at every microscopic level. Electromagnetic and quantum interactions determine how matter resists compression. But gravity creates the vast pressure profile within which those interactions operate. Earth is also almost, but not exactly, spherical because gravity pulls large bodies toward hydrostatic equilibrium. A sufficiently massive object tends to settle into a shape where its surface follows an approximately equal gravitational plus rotational potential. Rotation complicates the result. Earth bulges at the equator and is slightly flattened at the poles. Fast rotating stars can become noticeably oblate. Small asteroids, with weak self-gravity, can remain irregular like potatoes, dumbbells, or rubble piles. Gravity provides a kind of sculpting threshold. Below it, material strength can preserve jagged shapes. Above it, self-gravity increasingly rounds worlds. Mountains themselves have gravitational limits. Make a rocky mountain high enough and pressure at its base becomes enormous. Rock deforms and flows over geological timescales. On a small moon or asteroid with weaker gravity, a mountain can be proportionally taller. Olympus Mons on Mars rises far higher above its surroundings than any mountain on Earth, partly because Mars has lower surface gravity and lacks Earth's active plate tectonic recycling in the same form. Gravity shapes landscapes even when erosion, volcanism, ice, and tectonics do the visible work. It drives rivers downhill because water moves toward lower gravitational potential. It helps pull glaciers from high terrain toward lower elevations. It causes landslides when gravitational stress overcomes friction and material strength. It makes sediments settle. It allows hot, buoyant material and cool, dense material to circulate when density differences appear in a gravitational field, contributing to convection in atmospheres, oceans, and planetary interiors. Without gravity, up and down would lose their ordinary physical meaning. Atmospheres are particularly elegant gravitational structures. Gas molecules move rapidly in all directions. Temperature gives them a distribution of speeds. Gravity prevents most of Earth's atmospheric molecules from simply escaping into space, while pressure decreases with altitude because less atmosphere remains above. The atmosphere does not end at one sharp ceiling. It thins gradually. Light molecules are more likely than heavy ones to reach escape speeds in the upper atmosphere, especially at high temperature, which is one reason planetary size and temperature influence atmospheric retention over geological time. A small hot world has difficulty keeping light gases. A large cold world can retain them more easily. Escape velocity expresses part of this relationship. From Earth's surface, ignoring atmosphere and rotation, an object would need a speed of about 11.2 kilometers per second to escape Earth's gravitational influence without further propulsion in the simple two-body picture. Escape velocity does not mean engines must instantly launch a spacecraft at that speed. Rockets accelerate over time and can continue adding energy as they climb. Nor does escape mean gravity becomes zero afterward. The spacecraft still feels Earth's pull. It simply has enough mechanical energy that Earth cannot bring it back in the idealized problem. The escape speed from the Sun at Earth's distance is much larger than the escape speed from Earth alone. Interplanetary flight is therefore a dance among several gravitational fields. Mission designers exploit those fields. A spacecraft passing near a moving planet can exchange energy and angular momentum with the planet through a gravitational assist. In the planet's own frame, the spacecraft approaches and leaves with roughly the same speed in an ideal flyby, merely changing direction. In the Sun's frame, because the planet itself is moving, That redirection can increase or decrease the spacecraft's heliocentric speed. The planet's orbit changes too by an immeasurably tiny amount. Voyager used gravity assists to visit the outer planets and gain enough speed to continue toward interstellar space. Modern missions use similar techniques to reach Mercury, Jupiter, asteroids, and other difficult destinations without carrying impossibly large amounts of fuel. Gravity can be obstacle and transportation system at the same time. There are also special locations where the gravitational influence of two large bodies and orbital motion combine to create useful patterns. These are Lagrange points. In a rotating frame associated with two orbiting masses, there are 5 positions where a much smaller object can maintain a relatively fixed configuration with respect to the two larger bodies, with varying degrees of stability. The James Webb Space Telescope operates near the Sun-Earth L2 point, about 1.5 million kilometers beyond Earth in the direction away from the Sun. It does not sit motionless at a magical point where gravity vanishes. It follows a large halo orbit around the region, using occasional station-keeping maneuvers. The geometry keeps the Sun, Earth, and Moon on roughly the same side of the observatory, which helps Webb's sun shield maintain the cold environment needed for infrared astronomy. Again, gravity shapes engineering. The same equations that describe planets can be used to park a telescope in a dynamically useful part of space. On Earth, engineers rarely need general relativity, but gravity enters almost everything involving structures or fluids. A building must support its own weight. A dam must withstand the pressure of water, whose depth-dependent force ultimately arises because gravity gives the water weight. A suspension bridge carries loads through tension and compression in a gravitational field. An airplane generates lift partly to counterweight. A submarine adjusts buoyancy. A hot air balloon rises because the surrounding denser air experiences a pressure gradient in Earth's gravity, producing a buoyant force. Even a candle flame looks different in orbit. On Earth, hot combustion products are less dense and rise, drawing cooler oxygen-rich air inward and creating the familiar elongated flame. In microgravity, natural convection is greatly reduced. A flame can become more spherical and behave differently. Gravity helps give fire its ordinary shape. The human sense of balance is also calibrated to it. Inside the inner ear, the vestibular system contains semicircular canals that sense rotation and otolith organs that respond to linear acceleration and head orientation relative to gravity. Tiny calcium carbonate crystals add inertia to membranes over sensory hair cells. Tilt the head and gravity shifts the load. Accelerate forward and inertia produces a related signal. The nervous system combines this information with vision and signals from muscles and joints to infer orientation and motion. In orbit, the persistent gravitational reference sensed on the ground disappears from everyday experience because the spacecraft and body are falling together. The brain must adapt. Some astronauts experience space motion sickness during the transition. Then, after returning to Earth, gravity has to be learned again. A force so constant that you stop noticing it becomes obvious when the nervous system has spent months without ordinary weight. There is also a philosophical temptation around gravity that science handles carefully. Because general relativity describes gravity geometrically, one sometimes hears that gravity is not a force. In one useful sense, that is correct. A freely falling object follows a geodesic and experiences no proper force from gravity. An accelerometer in free fall reads 0. But in everyday engineering and in Newtonian approximations, calling gravity a force remains perfectly valid and useful. Even within relativity, physicists may speak informally of gravitational forces, in particular coordinate descriptions. The deeper lesson is not that one vocabulary is forbidden. It is that the meaning depends on the framework. Newton asks what force changes the motion. Einstein asks what geometry defines inertial motion. Both lead to the same practical answer in weak fields. The conceptual difference becomes important where space-time curvature cannot be ignored. The word gravity therefore spans several layers of description. Your weight on a scale, the acceleration of a falling object, the Newtonian attraction between masses, the geometry of space-time, the hypothetical quantum interaction of gravitons in a weak field expansion, the growth of cosmic structure. These are connected, but they are not all identical statements. One of science's achievements is learning when to use which layer. Modern experiments continue testing the foundations. The equivalence principle has been tested with extraordinary precision using torsion balances, lunar laser ranging, atomic interferometry, and space missions. If different materials fell at detectably different rates in the same gravitational field, it would signal physics beyond general relativity and would shake one of the theory's foundations. So far, no convincing violation has been found. Antimatter offers another question. Does antimatter fall downward? General relativity and the standard framework strongly expect antimatter to respond to gravity in the ordinary attractive direction. But direct experiments are difficult because antimatter annihilates on contact with matter and electromagnetic forces easily overwhelm gravity. Experiments with trapped antihydrogen at CERN have now observed its behavior under Earth's gravity and found it consistent with downward gravitational acceleration, excluding simple scenarios in which antihydrogen would fall upward with equal magnitude. The result may sound unsurprising. Sometimes the value of an experiment is precisely that it tests what the theory says should be unsurprising. Gravity has repeatedly survived such tests. That survival does not prove general relativity must be the final theory. Newton survived thousands of tests before Einstein revealed its limits. General relativity may also be an approximation to something deeper. Researchers search for deviations in black hole waveforms, pulsar timing, cosmology, equivalence principle experiments, laboratory tests of the inverse square law, and other systems. A new theory would have a difficult job. It would need to explain whatever new phenomenon motivated it while reproducing the enormous set of old results that general relativity already gets right. Mercury must still process correctly. GPS must still work. Gravitational waves must still propagate as observed. Binary pulsars must still lose energy at the measured rate. Light must still bend appropriately. Black hole shadows must remain consistent. Cosmic structure must still make sense. Replacing a successful theory is harder than inventing a new equation. The new theory must inherit the successes. This is why gravity remains both solved and unsolved. For the motion of planets, solved. For precision clocks around Earth, solved. For gravitational waves from black hole mergers, astonishingly successful. For the microscopic quantum nature of spacetime, unsolved. For the identity of dark matter, unsolved. For the nature of dark energy, unsolved. For what replaces classical singularities, unsolved. For why the constants of gravity have the values they do, unanswered at a deeper level. Science can hold those statements together without embarrassment. Knowledge is not all or nothing. A map can be extremely accurate across continents and still contain a blank coastline. Gravity's map is enormous. Its blank regions are among the most interesting places left in fundamental physics. One way to see how all of these scales belong to the same story is to trace the chain inward. Start at the largest scale. A web of galaxies stretches across the observable universe. Gravity grew that structure from tiny, early irregularities. Inside one filament lies a group of galaxies. Inside one galaxy, gravity guides hundreds of billions of stars through a halo dominated by dark matter. Inside one arm of that galaxy, a star formed when a gas cloud contracted. Around that star, a disk assembled planets. One planet became massive enough to hold oceans and atmosphere, differentiate into core and mantle, and become nearly spherical. A large moon raised tides. Those tides slowly changed the planet's rotation. On the surface, rivers found lower ground. Trees built trunks that could stand against weight. Animals evolved skeletons and muscles inside a constant downward field. Much later, one species learned to measure falling objects. It watched planets. It built clocks. It noticed a tiny error in Mercury's orbit. It discovered that time and space were not rigid. It built 4-kilometer laser instruments sensitive to changes smaller than a proton. And spacetime answered with a chirp from 2 black holes 1.3 billion light-years away. The scale of the story is almost difficult to hold at once. Yet no step requires gravity to change its identity arbitrarily. The same general principles repeat. Mass energy shapes spacetime. Matter and light move through that geometry. Differences in gravitational field create tides. Changing distributions of mass create gravitational waves. Dense concentrations bend light. Collapse creates stars, neutron stars, and black holes. On the largest scales, the equations participate in cosmic expansion and structure growth. The details become richer with scale. The underlying connection remains. Now return to your own body. If your mass is around 60 kilograms, your weight near Earth's surface is roughly 600 newtons. If your mass is different, the number scales with it. But that number is not the most interesting thing happening. Earth is not a flat platform under you. It is a rotating planet falling continuously around the Sun. The Sun is moving around the center of the Milky Way. The Milky Way and Andromeda move within the local group. The local group participates in larger cosmic flows shaped by surrounding mass. There is no absolute stationary platform beneath everything. Motion is relational, yet you can rest. The support beneath you pushes upward just enough to stop your body from following a free fall path through Earth. Atoms in the mattress resist being compressed into atoms in you. Electromagnetic interactions provide the contact force. An accelerometer would register that support as proper acceleration. The sensation is ordinary because you have known it your entire life. But in Einstein's language, it is remarkable. You are being held away from a geodesic. If the support vanished, for one brief moment you would be closer to inertial motion, not farther from it. The old question returns. What does gravity feel like? A falling astronaut feels almost none of the ordinary sensation of weight. A person standing still feels pressure from the ground. Gravity is easiest to notice through what prevents falling, through what falls differently across distance, through what curves, orbits, stretches, redshifts, and delays. Perhaps that is why it could remain mysterious for so long. It is everywhere and yet often invisible. You cannot block it with a wall. There is no known gravitational shield. Put a metal plate between you and Earth, and your weight does not disappear. Put a mountain over a laboratory, and Earth's gravitational field still passes through. In fact, the mountain itself adds a tiny gravitational influence. Every mass participates. The planet does not know which atoms belong to you and which belong to the bed. The field responds to the whole distribution. That universality makes gravity simple in one sense. There is no gravitational chemistry. Iron and oxygen do not possess opposite gravitational charges. A kilogram of feathers and a kilogram of lead, in the same location and ignoring air, share the same free fall acceleration. Composition becomes almost irrelevant to motion. And that simplicity led Einstein to geometry. If every freely falling object traces the same space-time structure, perhaps gravity is not a property added separately to each object. Perhaps it is a property of the arena they all share. From that thought came one of humanity's most successful theories. It predicted things no one had measured in 1915: gravitational redshift, the precise additional precession of Mercury. the stronger bending of starlight. Gravitational waves. Black hole solutions followed from the equations. Expanding universe solutions followed. Some predictions seemed so strange that even their creators doubted their physical reality. Then instruments improved. Atomic clocks climbed towers. Radar signals passed near the sun, pulsars ticked in binary systems. Lasers crossed vacuum tubes. Radio telescopes linked across the planet. The strange predictions became measurements. This is one reason gravity is such a beautiful scientific story for a quiet night. It contains familiarity without simplicity. A child drops an object and sees the beginning of the problem. A physicist studies quantum spacetime and sees that the end of the problem has not arrived. Between them lie 4 centuries of increasingly precise questions. Newton did not fail because Einstein came later. Newton found a pattern so powerful that it still guides spacecraft. Einstein did not finish gravity because quantum theory remains unresolved. He found a deeper pattern whose predictions continue surviving tests. A future quantum theory, if it comes, will not make the moon stop obeying Newton or GPS stop obeying relativity. It will contain those successes as limiting cases. Science advances less like replacing one story with an unrelated one and more like discovering that a familiar map belongs inside a larger map. Tonight, the largest map still has unfinished edges. Somewhere in the mathematics of black holes and quantum fields, information is asking how it survives. Somewhere in cosmological data, dark matter is revealing gravity without revealing its identity. Dark energy is changing the expansion of the universe without telling us what it is. At the Planck scale, our usual picture of smooth spacetime may fail, but no experiment has yet shown us exactly how. These are not gaps that require the listener to solve anything tonight. They can remain open. Gravity will continue working whether or not the final theory has been written. The moon will continue falling around Earth. Earth will continue falling around the sun. The sun will continue following its path through the Milky Way. Ocean tides will move along coastlines. Clocks at different heights will accumulate tiny differences. Distant galaxies will bend background light. Somewhere, 2 compact objects may be spiraling closer, losing energy into waves that will cross space long after tonight is gone. Some of those waves may already be passing through you. Gravitational waves cross Earth constantly from distant sources, though almost all are far too weak for current detectors to isolate individually. They do not shove the body noticeably. They do not make the room tremble. They change separations by fractions beyond ordinary perception and continue outward. Spacetime is not perfectly still. The quietness of gravity is partly a matter of scale. Earth's field seems constant because Earth changes slowly on human timescales. The sun seems fixed because one orbit takes a year. The moon's recession is centimeters per year. The Milky Way's orbit takes hundreds of millions of years. A black hole can wait billions of years between meals. Cosmic structure grows across ages. Gravity is often powerful through patience. It does not need sudden violence. A tiny acceleration acting continuously can move a planet across an orbit. A slight excess of matter in the young universe can, given billions of years, become a galaxy cluster. A tidal torque too small to notice today can, over geological time, change the length of a day. A dense cloud can contract slowly until fusion begins. The universe is full of consequences accumulated from gentle persistence. That may be the most fitting way to return to the surface beneath you. Earth's gravity near you is not changing dramatically from second to second. It does not need attention. Your body has already adapted to it. The bed carries your weight. The floor carries the bed. The building carries the floor. The crust beneath the building carries the structure, while pressure and material strength distribute the load through rock. Deeper still, the mantle sits under immense pressure. The core is compressed by the mass above. The entire planet holds itself together under its own gravity while traveling around a star. And none of this requires a conscious effort from you. The physics continues without supervision. The numbers are useful, but they are not the only way to hold the idea. 6.67430 times 10 to the minus 11. 9.8 meters per second squared. 11.2 kilometers per second. 3 kilometers for the Schwarzschild radius of one solar mass. 10 to the minus 21 for a gravitational wave strain. Useful numbers. But the idea is simpler than the list. Things fall. Falling becomes orbit. Orbit becomes a clue. The clue becomes geometry. Geometry shapes clocks and light. Gravity builds stars. Stars leave compact remnants. Compact objects shake spacetime. Gravity gathers galaxies. The universe expands. Quantum theory waits at the unfinished edge. And here, on one planet inside that enormous structure, gravity feels like the quiet support beneath you. Not because the bed is pulling you downward, because Earth and you belong to the same curved spacetime, and the bed is preventing your free fall. The sensation that seemed least mysterious at the beginning has become the strangest one. Standing still is an accelerated state. Falling is, locally, the natural one. And that brings the opening thought back into focus. The surface is here. The planet is here. The moon is moving along its orbit. The sun is holding the solar system in its long gravitational architecture. Far beyond it, the Milky Way is moving with its neighbors through a universe shaped by mass we can see and mass we cannot. The equations keep extending outward from that simple scene. Their consequences continue on their own. A clock nearby will tick at almost exactly the same rate as another clock a little higher or lower, with differences too small to matter for sleep. The ocean will respond to the moon. Satellites will continue falling around Earth. Navigation systems will quietly correct their clocks for relativity. Laser interferometers will remain attentive to spacetime. Telescopes will watch galaxies distorted by invisible mass. And the support beneath you will keep doing the simplest thing in the story. It will keep you from falling. The same gravity that shapes a black hole's horizon is present here in its gentlest familiar form. The same gravity that organized the cosmic web gives weight to a resting hand. The same geometry that bends light around a galaxy lies beneath every ordinary trajectory near Earth. No separate law is needed for the small and the large. Only different approximations, different scales, and different ways of seeing the same universe. For now, the questions can remain where they are. What is dark matter? What is dark energy? Is spacetime fundamentally quantum? Does a graviton exist as a detectable particle? What replaces a singularity? How is black hole information encoded? There will be other nights for unfinished physics. Tonight it is enough to notice that one of nature's deepest mysteries is also one of its quietest companions. It has been with you through every step, every jump, every fall, every breath taken under an atmosphere held to a planet. It was here before life, before Earth, before the sun, before the Milky Way had its present form. It helped small irregularities in the early universe grow into the structures from which stars and planets could eventually form. And now, billions of years later, the result includes a room, a resting body, and a surface pressing gently upward. Gravity does not need to be felt as a pull tonight. It can be felt as support. The planet is beneath you. The universe is larger than it seemed at the beginning. And the question of gravity can be left unfinished. Sleep well. Good night.